So for, I guess, the last workshop in this series of workshops, we're going to talk about system design. So more of an overview, not really anything in depth here, but all the details about how we want to, I guess, expand our application once we've done the basic development. So we've made a front end application. We did a workshop on Vue just yesterday. And now what we want to do is actually make this, I guess, a full-blown application, and we want people to start using it, and we want it to, I guess, sustain itself. We want it to be scalable, and we want it to be efficient. All these nice software engineering principles. So that's what we're going to be talking about today. I have some slides to go through today. The document posted is pretty much the same thing as the slides. I've also linked the slides in the workshop forum on Discord. So yeah, we'll just go through some slides. First thing I want to go over is databases. Okay, so we made the front end. Most applications are going to need a database somewhere in it. So what is a database? Okay, it's long-term storage for your application. So when you have data that was created in your application, or I guess modified, and you want it to exist after, I guess, the session is ended. So after someone has used your application website and they close the website, close the browser tab, and they come back and it's still there, chances are that was stored in a database somewhere. Okay, so you would put things like user accounts, right? Login information in a database, a user's preferences, options for website, just the general content on your website would also go in a database, right? So if you made some kind of website that had posts or comments, right, those would all be stored in your database as well, because they need to come back after the session is restarted, right? You don't want to write comments one time in your application and then the next person opens it up and they have to start from scratch too, right? There's no comments there. Everyone should have the same comments, so they should all be stored in one database and they should persist across all sessions. There's a bunch of different kinds of databases. Here's some examples where you have MySQL, SQLite, MongoDB, Redis, GraphQL is a kind of a fancy, almost a database kind of thing. There's like a million different solutions for database storage. The most common ones being SQLite or MySQL or any SQL-based relational database. So looking at SQL, I guess that's kind of the main or the most popular way of using a database. It's a language. It has a syntax, right? We use it to query a database or to insert into a database. Okay, so for this example, we'll say we've set up some kind of SQL database. The schema here on the right is kind of how things are stored. So SQL works with tables. Okay, so your database could contain multiple tables, and the tables contain rows, or I guess entries, right? So I guess in this example over here, this schema, we have three tables. There's an employee table, department table, project table. This is like a corporate layout database. And then in the table, employee table, there's fields, right? There's name, job title, phone number, salary. And in the actual database, there would be a bunch of entries within this table that have these fields filled out, right? So there'd be one row that has name, whatever, job title, whatever, right? And they're all filled out. And the best part about these databases is we can have like hundreds of thousands, millions of rows, and they do it very efficiently behind the scenes for us. So we don't have to worry about programming any efficient data storage, data structures, or anything like that. It'll just take care of everything for us. Okay. And the power we get from, I guess, the SQL language is we can start to narrow down searches through our database. So here's kind of a general SQL query, we'd call it. So select is a keyword in SQL. It means we're searching for items in our database. And it's asking for first name. This syntax over here doesn't actually match up with this schema image. They're just kind of vaguely similar. there's no first name in this employee table. Maybe we would change this over here to name, like this uppercase one or something like that. But we're selecting names from the employee table. So from whichever table we want to query from. So it's saying from this table. And then you can use where, another, I guess, keyword in SQL, to supply some kind of constraint on what you want to search. Right. So in this case, it's the constraint is the hire date in this hypothetical table that it's searching through is 2000. Right. And you can do all sorts of complex queries in this where clause, where, I don't know, where over here, like where salary is greater than this, where phone number ends in these three numbers, where, right? There's a whole bunch of stuff you can do in there, and you can even nest queries. You can get really complex. Okay, so that's kind of the best way to store a lot of data and search through it relatively efficiently. Okay, using this stuff. Here's like another example of the syntax, I guess. There's keywords, right? Select from, where. You can order the results you get by, right? If you're asking for multiple results from your query, you can order them. And this is more, I guess, structure, right? Those are all names, ends in a semicolon. They don't have to be split like this. Usually either you see them in just one big line. Yeah, that's the syntax for SQL. Okay, so if you ever see these keywords, all caps usually, select from, where, you just know that that's some kind of database query. Okay, so it's selecting specific constraints from a database and getting the data from it, retrieving the data. So here's kind of an example. Here's just some code I had on my GitHub that is database queries. Right, so in this first one, inside, this is written in Go, but you do this literally any language. There's probably some kind of library that lets you do SQL queries, whatever you're making. Right, in this case in Go, it's this query row function, but you see I supply a SQL query here. Select star from days where ID equals, right? And then in this Go case, that's how I'm passing values to it. But that's just a string, that's a SQL query. And the gist of it is you pass it to whatever function and it's going to go query that for you, right? Down here, here's a different keyword. We haven't seen this one yet, insert. So it's the opposite of, I guess, or maybe not opposite, but usually you either select from a database or you want to insert something into a database. So the insert into is going to do that, right? So there's two examples in code there. Next topic I wanted to get to is APIs. So I guess we're kind of going to slowly move back the abstraction hierarchy here, zoom out a little bit. So an API stands for Application Programming Interface, which is a really broad term. Specifically, what we're interested in is REST APIs. So REST stands for Representational State Transfer. You're never gonna hear it called that ever again. I had to look up what it stood for because I literally never hear that. REST, you're gonna see that all the time. Okay, so REST is a style of API that commonly is used to transfer data between applications over a network. Okay, so there are application or APIs that do, I guess, you could just be code. You could call a library an API if you make the functions a certain way. Right? The API is very broad. It doesn't really mean much. A REST API does mean something, right? This is a specific implementation of an API. So the gist of it is there's going to be a server and a client over this REST API. There could be multiple clients, but there's a server that's hosting a REST API. And it's going to make endpoints available. Okay, we call them endpoints. It looks like a URL here, so maybe it's like this www.myapp.com / whatever. You can have as many slashes you want, /API, /this, /that. And then you name the endpoint. So in this case, it's called endpoint 1. And then your clients are going to make HTTP requests to that endpoint. Okay, so they're going to use it like a URL and either request data or I guess request to insert data to that endpoint. Okay, so there's different kinds of requests. There's GET requests. So the main purpose of a GET request is to retrieve data. POST, which is adding new data. put is modifying, and there's more. There's like delete. There's a bunch of different request types. But the general idea with this is they don't really mean anything on their own. Okay, these are just conventions that get is retrieve data and post is to put data in. The server really decides how to deal with these, right? So the client is going to construct some form of payload that consists of, like a header, and it has some information in it. It tells, okay, this is how much data I'm sending. This is the type. Maybe I want a GET request. So the request I'm sending you is a GET request, and I'm sending it to this specific endpoint. Then the server will say, okay, well, I get your request. I see that you're asking a GET request, and you've sent it to this endpoint. So I'm going to execute some code, whether it gathered the data for you that you want, and then I will send it back to you in another payload. That's the basic idea of a REST API. Okay, we're communicating between two different, server and client with these types of requests and these endpoints. Okay, there could be multiple endpoints. Client can send multiple requests, different types of requests to the same endpoint, right? There's a whole bunch of stuff you can do. It's really up to how you design it. And if you're designing it for communication between your own components, I guess the way you organize your data is really up to you. As long as you remember how you did it, it doesn't really matter how you do it. Okay. If you're interacting with publicly available APIs, right, there are APIs that companies make available that you can use. You'll have to read the documentation on how they expect you to request data or how to insert it, because it's really up to the implementation. So usually you'll find a documentation associated with API. So here's a little diagram. This is a nice one I found. It's just what I talked about, some clients, right? This REST API is kind of in the middle. It's like a black box. You can see there's some different requests. So this endpoint, this user wanted all users. This user had new user, update, right? And this is a GET request. So it's getting all users. This is a post, right? So new user, it's inserting a new one. A patch is another one you can do. It's like updating, right? They're sending that. This REST API is handling it, and it's doing the communication, in this case with the database, right? This is another good practice, is to hide your database behind a layer of abstraction here. That way, we kind of avoid the funny business of users directly requesting data from the database. It doesn't seem like it's a direct request, but if you're burying database requests within just like straight in your front end code, it opens you up for a lot of security vulnerabilities, especially if you're storing sensitive information in that database. So the common practice is to abstract it or obscure it with an API layer. That way you can filter through all these requests. So if these clients are sending bad data to you, or they're requesting bad data, you can filter that out. You don't even touch the database. And then you can send out some other signal that someone's trying to do some funny business. Okay, so that's the general idea of an API. Okay, it's fairly, I guess, vague or broad what it is, but the concept is there, and the implementation, really, the details, is up to you. Here's just another example of some endpoints. So like, I guess this is some pet API. Quite often you'll see, I guess, a number or something in your API endpoint. So if you need to select, in this case, a specific pet, right? You could supply some ID system that you've created within your API, and the user would have to know how to use your API. They'd have to know that, okay, well, I have to supply a number here. I want specifically 1, 2, 3, or maybe if they don't supply any number, it gets all of them, right? That's kind of up to you, right? Other ones, put, delete, post. Okay. Perfect. Next topic, microservices. Microservice, okay, this is kind of a buzz word, I guess. It's really just, in my opinion, designing your applications properly, or I guess modularly, right? So you're breaking up your application into smaller programs, right? They should be small. They should be microservices, not big services. And then you're communicating between them. So you're using like the concept of that REST API to connect these components. Okay, so I think it's fairly similar. It's the exact same idea as breaking your code up. Like if you're just writing a C++ code or C++ program, you're breaking it up into multiple functions. This is the exact same idea, except on a larger scale. Okay, and make sure you can modify, I guess, these microservices, make sure modifications a lot simpler and a lot less likely to affect, like to bring down the entire application. Okay, because chances are, if you're doing communication between these microservices, you're going to have checks at like each of these communication points. So where one service talks to the other service, you're going to say, okay, well, is this one actually, did it send me the right form of data? Did it send me any data at all? And that way, when you actually do break a microservice, you know where that, I guess, the broken part is. And you can fix that exact one. Or if you want to make a modification to it, you just affect that one service and you don't touch anything else, right? There's no like library dependencies or anything in between them. They're completely separate programs. So it's really useful. And this is pretty much how all modern, I guess, web apps are built, right? Here's, I guess, the next slide will show the difference here. The opposite of, I guess, microservice architecture is monolith architecture. So that's just building everything into one program or one application running on one server, right? Which is maybe the older way of doing things, but it opens you up to a lot of issues, right? If that server goes down, you're screwed. If you break one thing in your program and maybe it breaks compilation somewhere and your whole program doesn't compile, right? That's also not good. So moving away from monolithic architecture, you get to your microservices, right? So all these little small programs are working together. They're communicating. They each access maybe a different resource. Maybe they're all running on different servers, which is also, I guess, a useful part of it is they don't all have to run on the same computer because we're talking over the network. They could be on opposite sides of the globe and they still cohesively build this one application, right? That's the idea with that. So you can get some really complicated setups with this, right? At its basic level, you've just kind of abstracted the database away, right? In this case here, what do we have? There's some hypothetical user interface that talks with, in this case, an API, right? And this API is going to communicate with all these different microservices. And maybe each of these microservices accesses its own database, right? We talked about there's multiple kinds of databases and they all have their pros and cons. So if you wanted to use all of them, well, you could do it this way, right? And this API gateway is going to be smart and it's going to delegate whatever request it gets from this user interface to the correct database. And that way you get the pros of all these databases and you don't really have to deal with any of the cons, right? So that'd be the idea there. Not going for this. It will become this quickly. So we have to worry about not doing this. Right? Here's a cool little GIF I found. Apparently this is supposedly, I guess this is Netflix's network architecture. So all these little nodes are probably different services that are running. You can see this API handles a lot of the requests, right? So I guess there's some front end nodes, probably load balancers and things like that. And this API is really going to be directing traffic to these specific nodes where they got to go. So some interesting stuff there, right? This whole architecture, you can spend forever working on this stuff, and they do. And these companies spend millions and millions of dollars on this architecture, and you can get paid a lot of money if you understand this stuff and you can set it up properly. So it's good to think about. I guess we kind of mentioned this briefly, but if we're using these microservices, there's nothing preventing us from using multiple languages for these individual microservices, right? I can write one in Python. There's maybe some specific data science library I want to use in a Python program, but my main website's written in JavaScript, right? Well, I can break that Python part on its own, and I can just do some REST API between them, and it's like they're combined, right? I'm using two languages in one there. So use whatever language you want. I guarantee you it has some way to do HTTP requests or host a REST API. My favorite one is Go. It's the language I always tell people to look up and learn. It's very popular for this specific, I guess, this exact case. I guess a lot of microservice architecture is built on Go. And even like the programs we'll talk about in a second, like Kubernetes or Docker, are written in Go. So this is like pretty much what it's designed for. It's pretty fast. Setting up an HTTP server is super simple. Like this is all it is. This code here on the right. This is, I guess, these two lines sets up an endpoint. So this endpoint is just has no name, it's just slash, and it hosts the server. So if you were to open this link, you run this code in Go, you open this link in your browser, it'll hit that endpoint and it'll trigger this function, right? So it's super simple. And there's a ton of third-party libraries and stuff to do probably whatever you want to do with it, to be honest. It's also decently fast, right? Not quite C++ fast, but definitely nowhere near Python. So I like Go. If you want to do this stuff, it's worth learning. It makes it really easy. Okay, next topic, containerization. Okay, we're taking another step back here in the abstraction layer, zoom out one more. A container is basically, it's just a virtual machine, or it's a computer that's going to run this program for us. Okay, and its only job is to run our program. So it's like a little tiny computer that exists on top of our actual computer that only runs the program we tell it to run, doesn't do anything else. Okay, so they can be pretty lightweight. You're going to tell it how to start, so you can pick whatever operating system or programs are installed on this container. And then maybe you just stick your GitHub repo in there. You tell it how to build it, how to run it, and then you spin up this container and it does that. Right? Super simple. And the best part about this is we can start to duplicate this, right? If I want multiple instances of this program, this container running, well, I guess the programs that we look at in a second, they'll just do that for us. We spin up multiple containers that have the same image, right? Image is, I guess, the starting point. And we'll have multiple instances of that program running. The key point here being the networking between these containers. Okay, we still utilize the networking between them like any other computer. So they have ports, it has an IP, right? We can communicate to it. It can send things out of it. We can communicate between containers, right? They're just little tiny computers. So Docker is probably the most popular containerization program. Okay, it runs, I guess, this host on top of your operating system. So if you download Docker, it'll run, you can download for Windows, it'll just run. You download some images. Okay, so an image is like the starting point, I guess. Maybe a Ubuntu image. Or some images even have things set up on them already. Like you can find MySQL images that have the database already set up for you. And that way you just spin up that container and then you have a database. Okay. So yeah, it's going to run these little containers. The best part is you can send these, I guess, as long as someone has Docker, you send it to them and it'll run on their computer. Okay, because all the dependencies and the operating system specific stuff that's going on in there is contained within the container. All right, it's perfect. It's really good. Makes everything nice and easy. And it makes all the advanced stuff that you can start to do with this, I guess the possibilities that you can do with this stuff is endless. Okay, so what are we missing on here? Docker Hub. That's just a host for images. Oops, go back. If you wanted to go there, it just has a bunch of images that are already pre-made. Some of these companies host them themselves. So you can find like a million different operating system images on there. Tools like Kubernetes, okay, that's what we're talking about here. They can orchestrate many of these containers at once, right? So you have a tool like Kubernetes running, I guess, on top of Docker. So you're really another level out here, abstraction. You can get pretty crazy with this. Kubernetes is now going to start pooling these containers, right? So maybe you build you've split your application into microservices. So there's a database access microservice. There's a, I don't know, handle payment microservice. there's user authentication microservice. You split all these things up. You've put them in a container now. So you made an image that has all the tools and all the operating system stuff you need to run that microservice. Now you're going to stick it into your Kubernetes cluster, it's called. And it can dynamically, I guess, start and stop these containers for you and manage it. So you can tell Kubernetes that, well, I expect to get a lot of traffic to my authentication service. So actually, instead of just one microservice instance running for that authentication service, why don't you spin up 5 of them, right? That way, if I get a lot of traffic, like we're talking like Facebook level traffic or whatever, right? I can dynamically add more instances, right? If they're getting overloaded, or if they're not even being utilized, well, I can shut some down to save on resources, right? If you're paying for a server, you don't want to run them all at the same time. So shut some down if they're not being used, right? It can even manage the health of these containers. So if one of the programs or one of the containers crashes, it can recognize that, shut it down, spin up a new one automatically, and nothing changes or nothing happens to the outside, to the end user, right? It's really, I guess you can go really complex with this stuff. And this is what provides you with the seamless user experience that you get on like most websites. If you want to think like YouTube or something, very rarely do other issues with YouTube, at least for me, right? Videos usually work. It scales with traffic. There aren't really ever any busy days where the website's slow today because there's a lot of people using it. And that concept really is kind of something of the past. You don't really get that too much on bigger websites now. I think maybe like 10 years ago or so, you would say, oh, well, Facebook is slow today. There's a lot of people using it or something like that, right? But you don't really get that anymore because behind the scenes, this is all set up, right? There's load balancers, there's dynamically scaling microservices in there, and this is what's going on. It's all really cool, at least to me. This is the stuff I like. The Vue stuff and the HTML stuff, maybe not, but this is all really cool. So I guess overall, the thing to take away from this is the proper way, if you finger quotes, you can't really see me, but to create like your applications. If you plan on receiving sizable traffic, if you're trying to make money with an application, you expect a lot of people to use it, this is the proper way to do it. But obviously it's not necessary, right? There's a huge amount of work involved with setting something like this up, right? Setting your clusters, your container orchestration up, deciding what the traffic is going to be for all these microservices, splitting your program up like that, developing all these APIs. It gets really complicated really fast. And that's why these companies have such large budgets and such large dev teams. It's because there's tons of stuff to work on, right? But in the end, you create this like really robust system, and then the end user really never has any issues with it. And it's efficient, robust, right? That's what we're looking for. So I don't expect anyone to set anything like that up for a hackathon, right? Like for this one. But if you are thinking about these concepts actively while you're designing, right, it helps you if for some reason, well, let's say, for example, you do another hackathon after this, and commonly prizes will be like, oh, well, if you win this one, we'll provide you with $10,000 of seed funding for your project and you can continue it, right? In that case, if you actually intend on making some kind of profit out of this project, you're going to want to think about this stuff ahead of time. Because if you're not, you can kind of dig yourself into some holes, and it can be really hard to refactor things to get it to a state where you can scale it properly if you didn't account for that at the beginning. So I personally, in this hackathon that we're doing, Hackoween, I think it's worth it. Or, well, you'll definitely grade a little bit higher if you're showing that you're thinking about some of these things. Maybe if you split some portions of your applications up and you're communicating between them through APIs and things like that, or if you obscure your database behind an API layer, right? There's definitely points to be earned by doing that, but it's absolutely not necessary. Here's some links. These are in the document too, but if you look at any of these, I linked some SQLite database setup. SQLite's pretty easy. You don't need to host a server for it. It's just a file that exists on your computer. So if you want just a basic database, here's a couple guides to do it. So here's a C++ guide. Here's one for JavaScript. So if you want to just stick it in your Vue application, that'll work just like that. This tool here, Postman, this is really handy actually. It'll let you just create a blanket HTTP requests to test your endpoints. So when you make your REST API, you'll want to test it and you won't want to have to program a new application to test it every single time. So this will let you easily change what type of request you're doing, to what endpoint, what the payload is, the different values in the header, right? Very useful. HTML server, oh, that's not HTML, it should be HTTP server in Go. That's that Go example that I showed. That was really simple. It's just a little bit of a write-up on that and what it's doing. And also the link to Docker if you want to install Docker. It's pretty simple. You just run the installer and then you're done. And you can run any container on top of it. Okay, that is it. There we go. 4 workshops done. This one was pretty short. I would have liked to do some more, I guess, in-depth stuff, and maybe we will do that in the future, but I think we won't really need any of this for the hackathon, so just good stuff to think about while you're developing. So yeah, hopefully everyone has a fun time at the hackathon. I'm really excited. Yeah. Any last questions or anything before I shut it down? Typing. Let's see. No. Okay. Well, that'll be it. Thank you for listening to me ramble about this stuff for half an hour. I really like talking about this stuff, so if you want to talk with me about it more, feel free. I'm always open to discussing this kind of stuff. Awesome. Thanks for watching, everybody.